In this video, I'll take you through the mathematical basis behind the key properties of PCA. The first property that we'd like to show is that the Wi are orthogonal to each other. So we know that the Wi are eigenvectors of the covariance matrix. Therefore, sigma Wi is equal to lambda I Wi. And we also know that the covariance matrix is symmetric, so it's equal to its own transpose. And we want to show that the Wi are orthogonal to each other, therefore Wi dot Wj is equal to 0. To show this, I'm going to first consider the expression lambda j times Wi dot Wj. You can rewrite this by moving the lambda j next to the Wj, and then use the eigenvector equation to rewrite lambda j Wj as sigma Wj. And then we use the fact that the covariance matrix is symmetric, so replace it by its transpose. And then note that Wi transpose sigma transpose can be written as sigma Wi quantity transpose. And then the next trick is to use the eigenvector equation again to write lambda I times the dot product Wi transpose Wj. So we have lambda j times the dot product is equal to lambda I times the dot product. And if we move this all to one side, that becomes lambda I minus lambda j times Wi dot Wj is equal to 0. So that means one of these two factors in this product has to be 0. So either the lambda I is equal to lambda j or Wi and Wj are orthogonal. So this shows that if the eigenvalues are different, then the eigenvectors must be orthogonal to each other. The second property that we'd like to show are that the scores are uncorrelated. We'll again use the fact that the Wi are eigenvectors of the covariance matrix, and we'll also use the fact that the Si are the projected data. So Si is equal to x times Wi. And finally, you can show that since x is 0 mean, the Si is also 0 mean. And we want to show that the covariance between Si and Sj is equal to 0. So we can write down the sample covariance of scores in this form. The second term disappears because the Si are 0 mean. And we'll replace Si by xwi to have this form of this equation. And just as in the previous derivation, replace xwi transpose as Wi transpose x transpose. And now you can see you have this x transpose x in the middle, which should remind you of the covariance matrix. If you take the 1 over n samples factor out front as well, you can just replace this all by the covariance matrix sigma. And use the eigenvector equation again to replace sigma Wj as lambda j Wj. So now we have the covariance of Si Sj is equal to lambda j Wi dot Wj. And since we know that the Wi's are orthogonal from the previous key property, we can show that this is equal to 0. So this means that the scores, again, the projected data, are uncorrelated with each other. Now notice if we look at the covariance of Si and Si, remember that's the variance of Si. And you can follow essentially the same exact derivation up until this last step. Just replace all the j's with an I, and you get the variance of Si is equal to lambda I times Wi dot Wi. So in this case, Wi dot Wi is equal to the norm of Wi, and since we assume that it's been normalized already, that means that the variance is equal to lambda I. So this shows that the variance of the scores, again, the variance of the projected data, is exactly equal to its corresponding eigenvalue.